Okay, in this lesson, we're going to be looking at the megastat output to compare to do hypothesis testing with comparing the means between two independent groups. So let's take a look at this right over here. We're going to read through the prompt. Customers at Food Town Supermarket have a choice when paying for their groceries. They may check out and pay using the standard cashier-assisted checkout, or they may use the new fast lane procedures, or self-checkout if you will. The store manager would like to know if the mean checkout time using the standard checkout method is longer than using the fast lane with an alpha of 0.01. The time was measured from when the customer enters the line until the time all of his or her bags are in the cart. For the standard lane, the sample mean is 5.5 minutes or 5.5 minutes, or 5 minutes and 30 seconds, if you will, with a sample size of 50. The population standard deviation for the standard lane is 0.4 minutes. For the fast lane, the sample mean is 5.3 minutes with a sample size of 100. The population standard deviation for the standard lane is 0.3 minutes. So you can see over here, I've got this information in Excel. I've got this labeled mean, standard deviation, number, and then this is the label. So I've got the standard lane, 5.5 minutes is the mean, 0.4 minutes is the standard deviation, and the number in that sample is 50. Okay, so then we also have the fast lane, 5.3 minutes. 0.3 minutes is the standard deviation, and the sample size is 100. So I'm going to click on data, and I'm going to click megastat. Then I'm going to click on hypothesis test, and I'm going to compare two independent groups. So just to compare two independent groups is where we're at right now. So we are not doing data input. The reason why we're not doing data input is because we don't have all of the data. What we have is a summary. So I'm going to put in the summary input. So I just highlighted the summary input for the first group, which is the standard group. Now I'm going to highlight the summary input for the second group, which is the fast lane group. So the hypothesized difference is 0. And the alternative hypothesis, which we should have stated the alternative hypothesis first before we did this portion. But the alternative hypothesis is that the mean of the standard is greater than, so the mean of the first group is greater than the mean of the second group. Okay. So, and then we've got a choice of whether or not we're going to do a t-test for pooled, a t-test for unequal, or a z-test, and we're going to do a z-test. The reason why we're going to do a z-test is because the population is very large. The population that we're working with, sorry, not the population, the sample that we're working with is very large. It's a sample of 150. And so as we get close to 200, it gets closer and closer to the z-distribution anyway. So as our sample size gets larger and larger and larger, the benefits of utilizing a t-distribution decrease. So our population, or our sample size, is large enough that we can use the z-distribution. Okay, so I'm going to click on all that, and I'm going to click OK. And you will notice that this is pretty close. The only thing that's different is I've got only one p-value instead of all three. So let's take a look at this. First of all, what is the null and alternative hypothesis? So let's zoom in here. Hold on. Having trouble zooming. Okay, so the null hypothesis is that the mu of the mu sub s, or mu of the standard lane, is less than or equal to the mu of the fast lane. So that's the null hypothesis. And the reason why that's the null hypothesis is because the alternative hypothesis is that the mu of the standard lane is greater than the mu of the fast lane. So you see mu sub s and mu sub f. F is the label for fast, s is the label for standard. And remember, this arrow is always going to point in the direction of the critical value. So when we have the alternative hypothesis that says mu sub s is greater than mu sub f, the diagram here is going to have the tail in the right hand side, or the critical value is going to be in the right tail. So the next thing that we look at is what is the level of significance. The level of significance is 0.01, and we get that from right in here. However, so point alpha of 0.01, sometimes you are not going to get an alpha. If you are not given an alpha, you need to choose what alpha you want to use and go with that. Essentially what you're saying is what level of type 1 error am I willing to accept? Or in other words, what is the probability of rejecting the null hypothesis when the null hypothesis is actually true? With 0.01, you've got a 1% chance of doing that. With 0.1, you've got a 10% chance of doing that. With 0.05, you've got a 5% chance of doing that, of accepting the null hypothesis, you've got a 5% chance of rejecting the null hypothesis when the null hypothesis is actually true. But here it's a 1% chance. So what is the test statistic that we're using? The test statistic that we're using is Z. And then the decision rule, before we can do the decision rule, we need to find out the critical values. Okay, so the critical value, let me pull this up really quick. Let's see, file, open, here we go, critical values. So this is for a one-tailed, right-tailed test, and 0.01, the critical value for 0.01 for a one-tailed, right-tailed test is 2.326. 2.326. So the decision rule is we are going to reject the null hypothesis if z is greater than 2.326. So let's graph this right here. We put alpha of 0.01 and we've got the z critical of 2.326. Right now we're not looking at the green, we'll look at that in just a minute. But the z crit is 2.326. And we're rejecting the null hypothesis if it is past 2.326. We are failing to reject the null hypothesis if it's less than 2.326. So what is the value of the test statistic? We go up here and we find that z is equal to 3.12. So the value of the test statistic is 3.12. And what is the p-value of that? Since we're doing a one-tailed right-tailed test, or a one-tail upper-tail test, the p-value is 0.0009. 0.0009, and so we put the p-value right here, and that is the probability of randomly getting a t-score of 3.12. So we come over here, we plot 3.12, the probability of that is 0.0009, and what we do now is we reject the null hypothesis because t-calc is more extreme than t-crit, or another way to do this is the p-value is less than the alpha. Either one of those will work. So if the p-value is less than the alpha, then we reject the null hypothesis. If the z-calc is more extreme than the z-crit, then we reject the null hypothesis. So what does this mean? What this means is that if you go back up here, you'll see that there is a difference between the standard and the fast lane of 0.2 minutes. 0.2 minutes. So what we're saying is the difference of zero point 0.2 minutes is too large to have occurred just by chance. We conclude that there is strong evidence the fast lane method is faster. So right here, 3.12, that's strong evidence. The probability of that occurring, that's a p-value of less than 0.01. I mean, that's less than 0.001. So that's really strong evidence that the fast lane method is faster. And one of the reasons why we have such a strong z-calc is because we're using a very large sample. We're using a sample of 150, and so when you have a sample of 150 and you get a result from that, it's going to be a heck of a lot stronger. It's going to be a lot better than, say, a sample of just 15. And your p-value is going to be a lot stronger. So that is the third example. I wish that there was ways for you guys to comment and ask questions about this. I'm going to see if there's a way to do that. If there is, I think there's a way for you to comment on these videos. So if you have questions about the video, comment below and I will get back to you. Cool. Thank you guys.